Hello, everyone. My name is Julie, and from the University of Oklahoma. Today, I'm honored to represent my study studying brown ocean and re-intensification of Hurricane Florence using CYGNSS and SMAP soil moisture data and numerical weather model. I'd like to acknowledge all my co-authors from their contribution and the support for this work. To start, what is a brown ocean? The brown ocean is an effect that when a tropical storm makes landfall and moves over warm and moist soils, it can get re-intensified because soils act like ocean to provide sustainable moisture and energy to the storm to grow. One of the most notable example of this brown ocean is the tropical storm Erin in 2007. It was initiated in the Gulf Coast, made landfall in the Texas border, and get re-intensified in the Panhandle area of Texas, dissipated in Oklahoma. It is a very rare case for Oklahoma to experience a tropical cyclone system, and it of course produced widespread damages there. Radar signals have confirmed the re-intensification of this storm and the ice structure in the Panhandle regions. Studies have found that one of the factors related to re-intensification is the moist soils because of precedent rainfall events. It provides the moisture and energy to sustain the storm intensity. Researchers have started looking into the mechanisms of soil rainfall feedback in the 90s. The diagram drawn by et al. In 1998 laid out the interaction of land and atmosphere. So basically, we have the wet soils moisture experiencing two pathways. One is a decrease in surface albedo, and the other one, the decrease in buoyant ratio, both of which can lead to the increase in total surface heat flux, such as sensible heat and latent heat flux. Of course, that has an impact on the decrease in the boundary layer depths. Then finally, it can lead to the increase in moist convection. A body of regional studies have confirmed the existence of brown ocean or the positive soil atmosphere feedback in different regions around the world, the global, United States, Australia, India, etc. With more and more observational network coming in, the direction of the feedback started to diverge because more studies found dry soils actually promote more rains. So it is not becoming an active debate. It points to uncertainty in our model simulation because previously those studies are based on a model simulation to investigate such interaction. One study published in Nature found the inconsistent results between satellite observations and model simulation. In particular, those model simulation points to positive feedback, while the satellite observation suggests a negative feedback between the soil and the rainfall rates. It is a motivation of our work. The overarching goal is to confirm the weight and soil moisture can re-intensify Hurricane Florence and reconcile the observation and model simulations. It has several impacts. The first, it is insightful for enhancing weather forecast scales. Once we know that initial soil moistures are playing a dominant role in those storm intensification or re-intensification, we are calling to acquire more accurate initial field of those data to initialize our model. And it has implication for surface hydrology. As you may know, those wet soils are conducive environment for flooding. Objectives of this study are to design a framework that compares soil moisture impact on storm from the observations and model simulations, to identify any feedback between soil moisture and storm intensity, to reconcile observation and model simulation, and lastly, investigate the timescale of soil rainfall feedback. In doing so, we acquired data from remote sensing products. So we had the satellite, the soil moisture product from CYGNSS and SMAP. They're basically similar in terms of the spatial resolution at 36 kilometer. But one of the advantage of CYGNSS data is that it provides sub-daily every 6-hour observation so that we can use that to investigate the land and atmosphere interaction. We had the remote sensing rainfall data set from the stage 4 at 4 kilometer and hourly resolution. Then for the model setup, we used the WRF version 4.3.2. On the right is showing the WRF domain of our experiments. To observationally quantify the feedback, we use the rainfall tracking algorithm called the model evaluation tool, mode time domain. It separates the rainfall field from different storm structure and tracking its evolution. So basically on the z-axis, you can see there's a time domain, and you can observe the different storm at different particular time in terms of its intensity, but also you can see the evolution of the storm across time. We did search the hourly rainfall intensity from the stage 4 data and identify those individual rainfall systems. Then we correlate those rainfall storm with antecedent soil moisture ranging from one day prior to those rainfall occurrence up to 30 days prior to the rainfall occurrence. Then finally, we calculate the correlation between antecedent soil moisture and the rainfall intensity. That leads to the main figure showing on the panel. So we had the antecedent soil moisture in the x-axis, the rainfall intensity on the y-axis from light rain up to heavy rain. Basically, we separate into two panels. The upper panel shows the very light rain, and you can see this is generally a negative correlation between soil moisture and antecedent soil moisture and the rainfall intensity. So we have this wetter soil produce less intense rain for the very light rains. But for heavy rains, we do observe some positive correlation, especially the 3-day antecedent soil moisture had the greatest impact on the rainfall intensity. That actually relates to the atmospheric moisture residence time in this region. But also see some negative correlation occasionally that is due to the typical drop in soil temperature that really impede the evaporation process. To confirm our observation, we use some models, WRF simulation to generate those experiments. We had designed the 3 experiments, 3 schemes. The dry scheme, we perturb the initial soil moisture by halving the field, and normal normal case is the keeping the initial soil moisture the same, and the wetter scheme that we multiply the initial field by 1.5. And on the right, it shows the WRF configuration, and we initialize the WRF simulation from 2 days prior to the landfall up to 7 days prior to the landfall. And this slide shows the results from WRF. As you can see, this on the left panel is the track simulated from WRF compared with the base track data. We did the WRF simulation did a pretty good job prior to the point at further inland. So we captured those landfalling process of the Hurricane Florence. And we see there's not too much difference between each experiment. We highlighted here the red line is a 3-day antecedent soil moisture. And on the right, we show some intensity matrix of the storm. So basically, there are minimum sea level pressure and maximum wind speed. The wetter soils, you can see, have the lowest minimum sea level pressure among the 3 in general, and the greatest maximum wind speed among the 3. We also highlighted the 3-day antecedent soil moisture that has the lowest minimum sea level pressure and highest wind speed, maximum wind speed among those experiments. We further investigated the rainfall intensity in different regions. We separated from rainfall core region, storm region, and the whole domain. For the rainfall core region, we say the wetter soils in the blue shaded area that produces a higher rainfall intensity than either dry soils or normal soils. But as you zoom out to the whole region, you can see the dry soils start to pick up. Actually, they have the drier soils have higher rainfall intensity among the three. From the WRF results, we see the wetter soils produces more intense and concentrated rainfall, but drier soils have less intense but widespread rainfall. It actually back up our observational analysis at the beginning. Finally, the takeaways from this study. Wet and thin soils can promote extreme rainfall rates, referring to the existence of the brown ocean effect. Wet and thin soils lead to intense and concentrated rains, while dry and thin soils contribute to light and widespread rains. The sign of the rainfall soil feedback is also determined by the soil temperature. So it's not only about the soil moisture, with warm soils pointing to positive feedback and cold soils to the negative feedback. But below, just summarize the findings from this schematic. We have a broad general brown ocean effect. We also have that is a positive feedback between soil moisture and extreme rainfall. We have energy limited brown ocean effect that when the soil is cold, it can produce lead to the negative feedback, and also water limited that is also a negative feedback that dry soils correlate well with widespread and light rain. With that, I would like to conclude and thank you all for your attentions. Let me know if you have any questions. Thank you.